Hang in there, you guys are doing good. Two satellites, mass 1 and M2, are on orbiting a planet with mass large M and circular orbits. The satellites travel in opposite directions with speeds v1 and v2 as shown in the figure above. Their orbital radii are r2 and r1. The magnitude of the angular momentum of the two satellite system is best described by. Okay, so we got a planet. Got two satellites in orbit. Are they going the same way or opposite ways? Yeah, I mean, this is actually going to be important because when you think about angular momentum as an idea, angular momentum is equal to r cross p. Now, normally we just solve for it in terms of r cross p and don't think about the directionality. But you actually have to use the right-hand rule here. So if we looked at the r, for example, for this one, if that's the r vector for this one, and this is the v vector, if I do rv, this angular momentum actually, for this guy, points out of the board. But if I do it for this guy, if I do it for this guy, I put my fingers in the direction of r and curl them toward v, this angular momentum would be into the board. So I think you're going to have to subtract. So angular momentum is going to be rmv. So I'm going to go with D on this one. We're going to go RMV for one, then we're going to subtract RMV for the other. Because angular momentum itself is RMV. And they're going to be in opposite directions. Like, ooh. Yeah. That was hard. I mean, not particularly hard, but challenging in its own way. Ooh, I like it. So it's the same problem. If U1 is the potential energy of the planet satellite system containing satellite M1, and U2 is the potential energy of satellite containing M2, which of the following best represents the U1 to U2 ratio? Okay. We can do this one, no problem. So we know U is equal to negative GM all over R. So is it U2 to U1? Is that what it says? U1 to U2? So I like this because it simplifies very quickly. The G's and the big M's and the negatives all go away. And you're left with M1 divided by R1 divided by M2 divided by R2. But if I'm going to take a fraction and divide it by another fraction, what's that the same as doing? This is from 4th grade math. If you're going to divide a fraction by a fraction, what are you really doing? You multiply by the reciprocal. Does that seem vaguely familiar? Do you guys remember that? Divide by a fraction is multiplied by the reciprocal. And so then I'm going to take M1 divided by R1, and now I'm going to multiply by R2 divided by M2. And end up with M1 R2 divided by M2 R1. Is that an answer? It is an answer. I wonder if that's, I hope that's the answer. Yippers. How many of these are there? Oh, there's only 9? We're going to do them all. That's really exciting for me. Come on, 8. Yes. Identical satellites X and Y of mass M are in circular orbits around the planet M. The radius of R, and the satellite X has an orbital radius of 3R. The radius of the planet is R, X is at 3R, and Y is at 4R. The kinetic energy of satellite X is Kx. In terms of Kx, the gravitational potential energy of the planet X system is, oh my God, what? All right, this one's at least 2 parts. This one's at least 2 parts. So one of the things that I want to realize right away here is that because it's in circular orbit, the centripetal force is the gravitational force. Which means that mv squared over r is equal to g m all over r squared. So v squared is equal to g m all over r. Is that cool? Where r is the orbital radius. Is that cool? So let's talk about the total energy of an orbiting satellite. It's going to be equal to u plus k. Our u is negative g m all over r, where r is the center-to-center distance. No problem. And what's the kinetic energy? It's 1/2 mv squared. Now, this is the part I want you to watch, because this is where the magic happens. Ready? When I go to write this, negative g m all over r, that's the same thing here. I'm going to write this 1/2 m. But didn't I just solve for v squared over here? What if I took this v squared and I put it in over here? What this tells me is that one way to express the total energy, so I have negative gmm over r plus 1/2 gmm over r. So what's negative 1 plus 1/2? So that is an interesting, okay, that is an interesting idea. Okay, that is an idea that this is a way to find the total energy. Okay, now this is not what the question is asking. Okay, the question is asking. It says, in terms of kx, what's the gravitational potential energy of the planet-satellite system? So we actually have to solve for this. So for this particular satellite, it's negative g m all over. What is its radius? 3r? How do we express the kinetic energy of this guy? So kx is equal to 1/2 mvx squared. Which is 1/2 little m. Ooh. So I wrote just the gravitational formula here. Negative GMM over 3R. That's for planet X. Or satellite X. When I write the kinetic energy for it, I can see it's equal to 1/2 times GMM all over 3R. This is Kx. So the question says, in terms of Kx, what is this right here? Yeah?
Are you missing a square on the GM over 3R term? Maybe not.
So V squared is equal to GM over
Oh,
R.
my bad. I just did these.
No, that's good. So because it's squared, I just plugged it in directly. Is that cool? All right. So I got to write this. U is equal to something Kx, correct? So Kx is 1/2 GMM over 3R. And so what is U? First of all, it's negative. How do we get from Kx to U? Well, this is 1/2, this is none. So I have to multiply by 2. So what's tricky about this problem is you have to know this thing. Before you go, so I'm not going to be here tomorrow. I'm going to have some work for you to do in here. Also, before Wednesday, I need you to do the B version for this, and there's going to be a free response that you were supposed to have done for today, but only 5 of you did it. I'm not enthusiastic about that. Then there's one for tomorrow night also. So get to work. There are many of you that are not working. You're going to have to start having some difficult conversations. You've got to get it together.
So you said that on the comment you said it put in terms of R of Earth or whatever.
Mm-hmm.
What does that mean? Like R of Earth equals something?
No, so your radius that you're solving for is equal to something times the radius of Earth.
Oh, so I gotta figure out that factor or whatever.
Yep.
By which I gotta multiply. Oh, alright. That makes sense. And I looked at my work right after I turned it in, and I was like, how can I be so stupid? Kinetic energy is not mv squared, it's half mv squared.
It happens.
Same with the square root.
What's up?
Not much, how are you?
Oh, what's happening?
Oh, not much, you got quite the setup here.
Barely.
How was your weekend? Do you guys have ninja stuff?
We're in baseball season,
Oh, that's right. I think I did see something like that on Facebook.
so, yeah, you?
Braden had some basketball, but it was, I don't even remember the weekend, to be honest with you. That's how I feel now. It's like I can't even remember what happened like 12 hours ago.
Oh my god, no kidding.
So I have a big favor to ask of you, and I feel bad asking it, but I need to anyways.
Okay.
There's a job posting in Chippewa Valley for a technology coordinator, and I would like
Exciting.
to apply for it.
Oh, you should 100% apply.
And I was wondering if you could write me a letter of recommendation. The only problem is the posting is only up for 1 week, so it ends on Friday. And they just posted it on Friday.
No problem.
Are you sure? I feel so bad asking, and I gotta go ask the